In this video, we will talk about the boundary conditions for advection equation. Suppose we have a problem where we need a boundary condition at x is equal to a or x is equal to b. And you can see that the advection equation is first order PDE. For time derivative, we already have one initial condition. But the problem is there is only one derivative for q with respect to x. So we cannot give two boundary conditions in this problem. But as you know that to solve a problem numerically, you need a boundary conditions at both ends. Otherwise, your MATLAB code or your Python code will not work in this way, or even in Mathematica, it will not work in this way. So we have to decide where to put, where to keep, where to uh, put the boundary condition either on x is equal to a or x is equal to b. That is the final aim of this video. So what we do? In the last video, we saw that how the characteristics look like, and we saw that the characteristics is something where the information travels. All the information travels in characteristics and you just memorize it once and for all. In the last video, we saw that x minus u bar t is equal to constant, which means that it is equal to constant x naught, and u bar t is equal to 2, for example. If the wave is moving from left to right, then we have u bar is equal to 2 and x is equal to x naught plus 2t. And if I solve this problem for t, x minus x naught, and t is 1 by 2x minus x naught. So this means that the characteristics look like this. Remember that to draw a characteristics, you need xt plane. And on the y-axis, we take t, and on the x-axis, we take x. And if you draw this, the slope is positive, and when x naught is 0, you get first characteristic, and when x naught is, for example, some other value, then you have y-intercept has some value, but we actually start from here. We cannot take it like this, right? So the characteristics are here. And we already decided that the whatever information is here, it will travel on this characteristics. And in the second one, if we have this characteristic, then the information will travel on this wave, in this way. So sound wave, for example, will travel on the characteristics here and here, so on. That is decided. Now, consider another option. For example, we have u bar is equal to minus 2. It means that the wave q, the wave of pressure or any other variable is moving from right to left. In that case, the u bar will be equal to minus 2 and x is equal to x naught minus 2t. And if we solve it for t, 2t x minus 2t minus x plus x naught, and t will be equal to minus 1 by 2 x plus x naught by 2. Okay, I think I made some mistake over here. It should be x naught over 2, but anyway, this is a constant c1 or c, or maybe you can add minus as well, since we do not want to make the characteristics on the negative t-axis as well. So this is just a constant. If you just draw this characteristic, this equation, that will be look like this. For example, it will, when x naught is 0, then we have negative you get characteristics like that. It depends where x naught is. If it is 0, so it should start, the characteristic should pass from the origin. So we have two things over here. Either your characteristic look like this, or either your characteristics look like this. And we remember, and I repeat, the Q always travel on this information. Based on this analysis, let me just talk about the boundary condition, how we decide a boundary condition. For example, if we have U bar greater than 0, if it is greater than 0, then we have characteristic like this. And this is the boundary. We cannot cross x is equal to a. And the boundary is, the x is equal to a is the boundary. And we have all characteristic look like this, right? When U bar is greater than 0, then the information at x is equal to, if you give information at x is equal to a, for example, you give a q a t is equal to 2, then it means that this 2 will travel on the this characteristic. If we have another value, this will travel on this way, so on. When you reach at the right boundary, so we don't need any boundary condition. The reason is this point, for example, if it is 3, then this 3 has the same value on the characteristic, which is 3. So Q B T will be equal to 3. So this means that we don't need boundary condition over here, since it is getting the value from the interior, and the interior has a characteristic, and the information is traveling on the characteristics. So when U bar is greater than 0, then we have boundary condition defined on AT that will be equal to some, for example, Q of T value, which can be a constant. Now look at the another perspective. Suppose we have U bar is less than 0. In that case, if we have a boundary like this, x is equal to a and x is equal to b, then all the characteristic will look like this with negative slope, so on. So whatever the information is here, it should be traveled on this characteristic. So it means that we should give boundary condition at x is equal to b. This means that QBT should be given Q of T, Q of B, for example. And when on x is equal to a, we see the characteristic, it is coming from the interior, so the information travel over here. So we don't need boundary condition at x is equal to a. So the boundary conditions are decided based on the characteristic. Now, wherever you give the boundary condition, this boundary condition is called the physical boundary condition. Physical boundary condition. And on the right hand side, where we don't need a condition, but it is coming from the interior, that is called the numerical boundary condition. Numerical boundary condition. Similarly, here at this x is equal to b, we required a, physical boundary condition. This is called physical, since we have to give some information on this side, and at x is equal to a, this will be called a numerical boundary condition. That will be numerical boundary condition. So in summary, I would say that when we have partial q by partial t plus u bar partial q by partial x0, if u bar is greater than 0 and we have initial condition with us, and if we have u bar greater than 0, we need this boundary condition q of a, And for numerical purpose, we will consider some other boundary condition. Not here, we cannot write it this way here. It should be defined in the code. And then if we have partial u bar is, if u bar is less than 0, then the initial condition is q naught, and the boundary condition will be defined at qb is equal to qb, which is a function of t and can be a constant. So these boundary conditions are required. Another boundary condition for numerical purpose will be taken from extrapolation. Thank you for watching.